There you go. So your DNA is being extracted at this moment. So just to let you know. All right. So again, welcome. Great to see everybody. I think we have an interesting meeting tonight. We have 6 presentations, and this is what I kind of like with the old members night / potpourri nights is just some short presentations from members who want to share various aspects of things that they're doing and what interests them. And it's a good opportunity for new members to see what people are up to. So the first presentation is by Shriya Naik. Hopefully I pronounced that properly, Shriya. And she she offered to talk about a book that she has read, and so it's always kind of nice to have a book review. So if you want to share your screen, Shriya, and tell us a little bit about this book and why you like it, why you would suggest that others pick it up, because it looks like a very interesting book.
Of course. So I'm just going to share my screen.
Okay.
And sorry for not turning on my camera tonight. It just lags with the audio and visuals. So hopefully I get a better computer soon so you can see my face.
Yep, no problem. Okay, that looks awesome. Okay, Shriya, I don't hear you right now.
Very quiet. She's muted.
Shriya, you have your microphone on mute.
How about now?
There you go.
Okay, great.
You better start over.
Yeah, I'm gonna start over.
Okay.
Okay, so I did a short analysis on advanced skywatching. It's the backyard astronomer's guide to star hopping and exploring the universe. The book is by the authors on the screen. So this is a hardcover book. You can find this on Amazon for $31.25. It has 288 pages. So a little bit about advanced skywatching. Advanced skywatching exceptionally provides a comprehensive and engaging text with colorful photographs and illustrations to help understand the universe that beckons above your backyard. So I believe the authors did a phenomenal job with the coordination of the topics and the subtopics in each chapter. They have included a descriptive explanation of each illustration and a brief introduction, along with an elementary text regarding the topic. So this is just the arrangement and style of advanced skywatching. So the image on the left shows a chapter page or introducing a new chapter. As you can see, it shows a vibrant image of phenomena and includes a quote on the bottom left corner over here, which is known to be expiring and associated with the image. And the image on the right shows the topic in the chapter. So in this case, meteors is part of chapter 5, other lights in the sky. And in this case, meteor is the main topic. And so far, no subtopics are shown, but the text is filled with information, such as the composition of the meteors, the types of meteors and the famous ones. They also talk about what makes them famous, as well as how to spot them in the night sky with your naked eye or your own telescopes. So more arrangement and style of the book. Again, the image on the left shows a topic of computer control and mostly talks about how you can put your computer to the best use to decipher, name certain constellations and other celestial objects like nebulae and other galaxies. The chapter also talks about the different types of extensions, apps, and features you can download on your computer, while including step-by-step tutorials. Okay, so the image on the right includes the star hopping concept, which was in the title of the book. And I'll explain it more on the next slide, but to be brief, this page has stood out to me because of its definition, quality, and the little details to imitate the night sky as if you were actually looking up. What I like most about advanced sky watching. So the chapter pages. The chapter pages include vibrant illustrations of phenomena such as bright nebulae, galaxies, and celestial bodies. I find the illustrations to be very helpful for beginner astronomers because it helps them decipher and familiarize themselves with certain objects in space. So chapter 2, Skywatching Tools, was one of my favorite chapters as the authors give a slowly but surely intel on how to use certain tools, including computers for astrophotography, as we saw in the last slide, and telescopes and accessories to have the best experience possible. So talking about moon filters and other filters. So more about the star hopping concept. It can provide a further understanding to amateur astronomers to spot certain celestial phenomena in the sky, like constellations, nebulae, galaxies such as the Andromeda Galaxy. And this chapter is very helpful because before every celestial object, the authors provide a reference code, usually consists of numbers and letters, and they correspond them onto the key maps. And I like the overall objective of advanced skywatching because the book overall provides enough information to observe and decipher information and objects with most confidence. I mostly salute this book for its illustrations and the sense of coordination. I recommend this book to aspiring amateur astronomers. Okay, so these are just some pictures I took out from one of the topics. So these are just some snips of Mercury from advanced skywatching. So I have included the topic as the title called Mercury, and underneath it shows a brief statement of Mercury, but not really an introduction. I find this statement to be very interesting and well written, as it is like none other I've ever, and it mostly sounds clever to me because it certainly does hook or attract the reader. Moving on to the far right, we have a text explaining the transit of Mercury and how to safely spot the transit through a telescope. We also have facts and more elaborate information about, as well as a clear image taken by the satellite who visited Mercury from space that took this miraculous picture. And finally, we also have this quote on, so there's a quote on each topic, and there's a particular quote on this topic from Mercury. And I find this quote to be very compelling as it provides a boost of motivation to continue what I love doing, which is astrophysics, and inspires me in such a way that I will never find the whole career concept and intention of astronomy boring. So I rate this book 5 stars, and I highly recommend this book to future aspiring astronomers with interest in astronomy, with every aspect of it as well. So astrophotography, computer coordination of stars, analysts, and observers. Thanks for watching.
Oh my gosh, thank you very much, Shriya. That's great. Any questions for Shriya about this book? I should mention that one of the authors, David Levy, gave a talk to our club a few years ago, and Alan Dyer is an amazing photographer out in Calgary who, if you don't follow his Twitter account, you should, because he's always posting great pictures. Any questions for Shriya? Okay, well that's great. I mean, the one challenge for people new to the hobby is how do I start? And a book like this looks like it's a perfect thing to grab onto, and as I say, it's a great Christmas gift for aspiring new astronomers. So
yeah, for sure. Thank you, Randy. Thank you.
Yeah, Shriya, I have a question.
Yeah.
Shriya, have you used the book to actually observe, like practically have you used it and been able to observe things with the help of that book or computer or
I've tried to. I haven't really used a computer with it. I plan on doing that when I get access to those electronics mostly. But I have used it to do basic sky watching, just like observing and deciphering some constellations. So yeah.
Okay.
Well, yeah, it sounds like you're taking the right track. I mean, there's so much involved in you know, if you're a beginner to this. But remember, we do have telescopes that you can borrow. and some of them do
Mhm.
have go-to capabilities, so you can
Right.
check that out
Yeah.
on your own. So great. Well, we look forward to observing with you sometime in the
Yeah,
future
for sure.
when we can all get together. It's so
Mhm.
frustrating, but yeah, that's great. So, Shriya, thank you very much for
Thank you. Thank
this
you for listening.
book review. And I like book reviews. I mean, I think they're great. There's so many books coming out these days. They're really, really useful. Actually, Alan Dyer and Terry Dickinson have just republished their a new edition of their Backyard Astronomer's Guide, and the first edition was great. So I'm sure this next edition is really awesome as well. So hopefully someone can review that for us at some point. All right. Well, Chris, you are next. Chris Malicki is going to talk to us a little bit about the proper motion of 61 Cygni. So this is an ongoing presentation from Chris over the first time he presented this was over like 200 years ago, talking about this proper motion of this star. So this is an update. So Chris, it's all yours.
Randy, first of all, tell me, can you see, is my screen being shared?
Yeah, it looks good.
Okay, so this is my third update. So those of you who have been in the club for a number of years might remember me giving 2 potpourri talks. The last one was about 3 years ago. The one before that about 5 years ago, about this rapidly moving binary star in Cygnus. I've been following the binary star 61 Cygni since the year 2014. I got really interested in it after I read this article in Sky and Telescope magazine in August 2014. I learned in that article that 61 Cygni is a very nice binary star. The 2 components are almost the same magnitude. They're a little bit 5.2 and 6.0. They're 31 arc seconds apart. And the star is one of the closest true binary stars to the Earth. It's only 11.4 light years away. The stars are smaller than the sun. And this historically, for ages, people thought that the skies were immutable. Now we know that things change. And this star is rapidly racing through the sky. And in only a few years, you can actually follow its motion. Its proper motion is 5.2 seconds. That's very, very fast. I mean, the fastest star that you could see a year-to-year motion is Barnard's star, which is about 10 arc seconds. And because the star is so close, it was the first star to have its parallax measured, so we know its distance. In Bessel in 1838 measured the parallax. So the second, so I got really intrigued reading this article. The second page of the article has these 3 diagrams. So look to the upper right. 61 Cygni is very easy to find. It's a nice little parallelogram with the Deneb, Gamma Cygni, and Epsilon Cygni. So it's really easy to find. It's a naked eye star, but certainly with binoculars, it's a piece of cake. In a large magnified view, the 2 stars are 30 arc seconds apart. And what's really interesting in 2014 is there's a background star, 10.7 magnitude, like the star is moving in this direction over the sky. And in 2014, it was the brighter component A was extremely close to a magnitude 10.7 star. And so the author of the article said, this is one way that you can, in real time, from year to year, see a star actually moving, the proper motion of a star moving across the sky. So in the lower diagram, they showed in 2014, the brighter star, the A star, and then the B star, and there's a 10.7 magnitude star. So 2 years later, the A and B stars were here, and actually this year, they're right here. So I figured, well, I'm going to observe this star at Starfest, because it's August, and just make a drawing of it. So I did that, and without going through a lot of detail, so in Starfest in August 2014, I made this diagram. A year later, I made this one. A year later, I made that one. So just very briefly, like the A and B stars are there, and there's the 10.7 magnitude star. That's the first time I observed it. A year later, here's my diagram, and the year after that, here it is. So I didn't use a reticle or or any measuring instrument. I just drew as carefully as I could by eye. And then when I got home, I measured the distance from A and B and A to C, and I figured out what is the average distance and the angle. And then 2 more observations in 2018. You could see the 10.7 magnitude star is quite a bit farther from A. And last month, I had another chance to finally observe it. So there's A, B, and C. So again, I measured, like on my rough diagram, this distance, that distance. I got the ratio. And I just turned everything in the same direction. So my first observation in August 2014, it's oriented the same way as the diagram. So there's A, B, and 10.7 magnitude. So here's A, B, and this is what it looked like to me. Now, in October 2021, 7 years later, like the stars are there. And so A, B, and look how far C is from A. So I summarized, I showed this slide in my last presentation in, I think, when I last talked about 61 Cygni to the group. So I made the background constant for A and B, and pretended that the background 10.7 magnitude star is moving. So in 2014 it was there, 2016 it was there, error of measurement 2015, and I calculated the ratio AB to A to the background star. So my measurements were in these years were 0.43, 0.45, 0.64. The predicted from that sky and telescope diagram were these numbers. So you know, within error of measurement and just rough crude diagrams, that's what I got. And now this is I put my latest one here. So this is my last slide. So again, here's 61 Cygni, the brighter star A and B. Here's the 10.7 magnitude star in 2014 as I saw it. And we've seen this already, 2015, 16, 2018 was there. And now it's this far away. And so in the 7 years I've been following this star, it is the A star has moved 36.5 seconds, arc seconds away from this faint star. That's the same as the diameter of Jupiter in the sky or the rings of Saturn. So in 7 years, you can see a remarkable change in the proper motion, and all fortunately because there was a faint background star so close to the binary. And so this is my latest measurement. I got 1.35 from the diagram. It'd be 1.5, but nonetheless, that's how far it's moved. So that's the end of my presentation, and I just wanted to give a further update. And I hope in a number of years I'll give yet a further update, like maybe 2027, 2030, who knows. Okay, thank you, everybody.
Hey, Chris.
Yes.
Were all these observations done in the same location?
They were either at Starfest or at my cottage near Midland. That's where I observed last month, near Midland from my cottage. They were all, with all of them, I used a 14.5-inch Dobsonian portable telescope.
Cool.
So 2 different locations.
All right.
Thank you very much, Chris. Any other questions? Of course, the position of the telescope will affect the observation.
Yeah. Well, I use the same telescope each time.
All right, but did you account for moving it from Starfest to the cottage?
You mean the parallax between Starfest and Midland compared to the...
I'm just kidding, Chris.
Yeah, I kind of thought so.
It's like,
I thought Dennis
you wouldn't be able to detect it probably, but
Dennis,
if you were across the country, you might.
Yeah, maybe from Jupiter or something. Any other questions for Chris?
Yes, I have a question. Chris, why don't you invest in a reticule of some kind so you can make more accurate measurements?
Well, you're the technophile, Fred. You're the one who makes
a Christmas present for you.
Yeah, and I'm very much a visual person, not a technophile. It would have been more accurate if I measured with a reticle. I understand. I'm not doing this for like a scientific observation. I'm doing it as a naturalist of the sky hobby type of thing.
It's a good point, though. Maybe bringing these different viewpoints together. Maybe we should encourage people to use reticle and see. This is definitely a star that many of us can find and watch over the upcoming years. And are there other fast-moving visual stars, whether they're single or double, that we can watch and measure? Because it really gives you an indication of the motion of stars through the galaxy, and that's the fact that you can Chris, you've been able to measure it yourself. That's really awesome.
Yeah, well, Barnard's is certainly the best one to do. It moves twice as fast, and it's got a really nice field of faint stars behind it. So that's the best one that I would encourage people to do. Barnard star and a Fuchsius.
Oh, Fuchsius? Okay, great.
Yeah, so it's a summer star.
Chris, if I can ask a question, the two stars are co-moving, but are they gravitationally bound to each other?
Yes, they are. They're dwarf stars. I looked this up before the meeting. They have a 650-year orbit, and in the year 2100 will be their farthest apart. They'll be 34 arc seconds apart. I don't know when the closest is, but yeah, they are gravitationally one system.
Great, thank you.
Okay,
yeah.
That's a good project for future Mississauga Center members to.
And neither of them, Chris, neither of those stars are at any point variable, right? I mean, there's no.
Well, they're orange K-type dwarfs. That's what my book says. As far as I know, they're not variable. So
there's nothing rotating. Okay.
Yeah,
it's a beautiful star. Double.
Yeah.
Oh, yeah.
I think
lovely. Yeah.
Everyone should just take an opportunity to observe them, let alone watch them over the next few years. But no.
And it's easy this one's very easy to find. It's as I showed the map in Cygnus, like it's a nice parallelogram with the northern part of the Northern Cross.
Yeah, it's for sure a beautiful star to look at.
Yeah,
I presume
summer.
I presume Bessel picked it to measure parallax because it was moving, but I wonder how 150 years ago, how the astronomers, or more than that, were able to notice a star was moving.
Yeah, I don't have the answer to that. I'd have to research that. Very good question, though.
He was probably using a reticule.
Yeah.
or the observer's handbook.
Yeah, could be.
Okay, I should mention that the new handbook is out, and Chris is an assistant editor for that, and does a lot of work. So kudos to Chris for the handbook.
Hello, Chris.
Yes.
Yeah, it's Chris McNeely here. I'm just curious. You have a 14.5-inch Dobsonian. What's your preferred eyepiece that you're using? 14 millimeter or?
No, I use an 8. Like I use a 35 to get a really nice wide field, and then I usually use an 8 to observe. My favorite thing are galaxies, so with an 8 millimeter, that's perfect for me. Get about 80 times magnification with that.
Okay.
All right, thanks a lot, Chris.
Okay.
Our next speaker is Shaquille Anwar, who saw that amazing aurora that many of us did not see but heard about. So Shaquille, the floor is yours.
Thanks, Randy. Let's get my screen set up. Okay, so yeah, today I'm going to give an overview and a recap of what I observed on the November the 3rd, the 4th, the Aurora, based upon the strong geomagnetic storm that we encountered that day, that night. So just as an overview, as a recap. So on the 2nd of November, a very strong solar flare erupted from sunspot AR2891. You can see that in the middle of the screen here. It caused ripples going far distance on the sun, and it was directly Earth directed. So the one thing about this flare, the CME that resulted from this flare, was that it was very fast moving, and it became known as a cannibal flare or the cannibal CME, because it swallowed up two CMEs that had preceded it, and those came from this sunspot here on the bottom right there, AR2887. So this was a pretty well photographed and complex sunspot. As you can see here, you can see the magnetic field in the plasma going up and down here. So this was quite it was quite beautiful to look at, actually, but then this one stole the show afterwards. So based upon the fact that it was a cannibal CME, there was a prediction that there would be a very strong geomagnetic storm and auroras as a result of this flare. So this shows a model of what was anticipated. We see here
Is it me or have we lost?
Yeah, now I don't hear him.
Okay.
We lost him.
He's frozen.
Okay.
Zoom freeze.
Get a little closer to that sunspot.
Yeah. Well, the sun has amazing power. So. Oh. Okay.
It looked like he was rebooting. He went away, so maybe he's rebooting.
Probably,
Yeah, we'll give him a few minutes to. All right. Tell you what. I'm going to give him a few minutes to regroup, and maybe we'll just go on to our next speaker, which is John Burgener. John, do you want to bring up your session and?
Yep, I can do that.
Hopefully, you won't get the ice cream freeze.
All right. Well, I may have some freezing problems too, but we'll give it a try.
You're among friends, so.
Yeah.
Shaquille, we're just gonna try another presentation here and be patient. We lost you there with it frozen, so.
Yeah, a lot of exciting things happening in the sun there.
I mean, the power of the sun is amazing. At the fact that it could just sort of blow you out of the water like that. So, hang tight. We'll get back to you, and John's gonna talk about his 3D program here.
All right, well, I've talked about comets and impacts and big comets and stuff several times. Trying to visualize it better. I just worked on a three-dimensional program which actually shows the debris falling on the Earth rather than just the debris flying out into space. So as long as my computer is working here, there we go. The question of the day is, can I show evidence that the Carolina Bays fit the scenario of an impact spewing out debris in the secondary craters caused by the debris forming the Carolina Bays? One of the features of the Carolina Bays is the more than one orientation, so you need to have more than one impact location. Generally speaking, the Carolina Bays are ellipses, such as this one down here, but they come in a variety of shapes, but they're all basically circles, ellipses, or skinny ellipses. Michael Davidus has been trying to convince the world for years and years that they are secondary impacts, and has been looking at a place called the Saginaw Bay, which he believes is an impact about 800,000 years ago and caused the Carolina Bays, but it only covered one angle. So he then looked around and found another depression just to the west of Lake Michigan and felt that the two of them 800,000 years ago would cause the multiple angles of the Carolina Bays, which is fine. I'm looking at bigger craters and bigger comets, even than his massive ones. And I found that there's 4 ellipses forming a depression in Lake Superior and Lake Michigan, and that you could probably declare all of those as one event that would certainly cause a lot of secondary debris. If you look at Orcus Patera on Mars, it's a long skinny feature which is labeled partly as a crater and partly as a G, we don't know what it is. But you compare that to the shape of Lake Michigan, the blue line here is Lake Michigan's 20-meter line, and the red line is Orcus Patera, and the stuff up here is clearly glacial striations, so that's not part of the same impact. And the outlines are almost identical. They're almost identical in length, width, and size. So if indeed Mars can have a crater like that, then possibly Earth could too. If you look at those 5 locations, they actually give a multitude of angles towards the Carolina Bays, but this lovely drawing didn't really convince anyone of anything. It wasn't enough. So I looked at iSail. iSail is a delightful program. It's geologically correct, and it does show that indeed a skip impact can happen wherein the comet hits the top of the Earth, half of the comet continues and half of the comet sprays out in debris. But iSail is very low resolution. It really doesn't solve the problem. What iSail will do is let us work out what the secondary debris craters would look like. So doing some iSail calculations of low speed, 3-4 kilometers per second, and low angles, you get a long skinny crater, a nice ellipse, a really good matching ellipse compared to the Carolina Bays, slightly elliptical, not so good, and then finally at around 40 degrees, you're into circles and not elliptical at all. If you change the different speeds, 2 kilometers, 2.5, 3, also 4 or 5, the shape of the crater doesn't change much. So speed is not the determining factor of the crater, it's the angle of impact. And if you look at all these things from iSail, you come to the conclusion that you're looking ideally for about 20 degrees and about 3 kilometers a second, but 12 to 25 degrees and 2 to 4 kilometers a second is about the right range of what we're trying to see if a comet could create that kind of a secondary impact. Now, back to comets and craters and asteroids. Generally speaking, craters are circular, almost perfect circles. And almost all crater experts will tell you that if it's not circular, it's probably not a crater. I wrote up a routine last year trying to show the number of angles that you get for things approaching the Earth if you've got a whole bunch of comets approaching. If the speed's right, you can actually have a comet come around the back side of the Earth and just hit the surface, but it depends on your speed. But 2D, it doesn't really do it either. So I did a 3D program. This one shows a wide array. Imagine thousands of comets this way and thousands of comets that way coming towards the Earth. And as they approach at different speeds, they hit different locations, forming different shaped craters. And these guys here are the interesting ones for me. Different speeds. This one is 60-kilometer comets at 30 kilometers a second. The previous one was at 3 kilometers a second. So slower speeds, they wrap around the planet. Higher speeds, they just smuck into the planet. But when you zoom in, you get some really odd shapes. The program is calculating these shapes simply as when the comet is hitting the bottom of the comet onto the Earth, you only got a little bit of a sphere touching, so it's a small circle. And as the comet gets deeper and deeper, you get up to half of the sphere. And then as it gets farther and farther towards the top, you get a small part again. These are the circles that are drawn according to the depth of the comet hitting the surface of the curved Earth. And these odd shapes, nobody would ever believe are craters, but indeed, that's what the program shows. They can be craters. Here's a different speed, a lower speed, 3 kilometers, and you get really strange shapes as you're approaching the 2 or 3 degree impact angles. So that's hopeful because Lake Michigan doesn't look like your standard circular crater. Last year, I had created I think it was 2 years ago, I created a program that showed the skip impact debris going off into space. Looks really neat. Still didn't solve the Carolina Bays problem. This year, the same program modified into 3 dimensions shows the debris falling on the Earth. And all these little things here are individual impacts from the secondary debris. You can zoom in and you actually see the shape and the orientation. And if you keep on zooming in, the program will give you the impact angles. So 20, 18, 15, 10, 16, and the speeds, 4.6, 3.6, 4, 4.1, 3.9. They're exactly in the range that one would need for the Carolina Bays. To be fair to Michael Davidis, I've also programmed in his impact event. A little harder to get the splash to focus out there, but it's doable. And if it's doable, then perhaps it happened. Again, you're getting the same kind of a range, 13 degrees, 12 degrees, 12 degrees, a little lower impact angle, but that's more a matter of the program than reality. Reality, they vary. You can get some like this one here at 44 degrees. So both scenarios would actually explain it. I had fun with the program. I included atmospheric drag, which is important. If you don't have drag, you don't get the right angles. So these little things here up there, there's no atmospheric drag heating them, but as they get closer to the Earth, they get hotter. And finally, if they land at a high enough speed, the program shows them burning. You get an effect like this, where you have your main impact and you have all the debris scattering around the planet and back again, with an enormous proportion of it coming in at high speeds and very hot, and probably causing an awful lot of fires and devastation to the planet as it comes down. So if this event happened, most of the planet would be adversely affected. And yet there's some areas like here in South America where almost nothing hits. The Pacific is almost nothing hitting. The Atlantic is almost nothing hitting. Eurasia has a lot hitting. Africa is very little, and Australia none. So it's not a planetary-wide extinction event as in Chicxulub type events, but it does affect a lot of the world. And most of the effect, Eurasia, North America, South America, and the Arctic, Alaska, and places like that. Creatures living up here are going to have a hard time of it. The program is dealing with waves. Waves are amazing things. They can be very focused. So here you have a very defined upper part of the wave, a very defined lower part, and all the debris is landing in one spot. Because the amount of studies done on skip impacts is virtually none, I can't say for sure what a comet impact debris wave would look like. But this is one potential. Another potential, if you imagine this is a comet plowing through the Earth, and that's the Earth heaving before it, you get forward motion and sideways motion. And again, it's still a reasonably restricted, but a lot less than the previous wave. And then you have waves, which are just waves, piles and piles of chaos and massive particles moving in all directions. And some of the comet event is going to be that too. So the program actually deals with 4 types of waves: a shock wave from the debris tossed in all directions, as the comet is pushing through the dirt, it's pushing stuff ahead of it at speeds similar to the comet or faster or a bit slower. And the bow wave, as it pushes sideways, it will then move the soil, the dirt, whatever, forward and sideways or just sideways. So I've got part of the program is doing a shock wave, part is doing a push ahead, part is doing a bow wave forwards, and part is doing a bow wave sideways. And again, it's not designed to be an exact rendition of what the waves would look like, because I don't know what they would look like. It's designed to show you options, and do the options include producing something like the Carolina Bays? And my answer is yes. Yes, it positively shows that you could do the Carolina Bays from this kind of an event. The program has all the previous stuff that I've been programming into the computer files for this kind of event. So there's 16 simulations. You can select them from a menu when you start up the program, and the program is available on my web pages at www.craters.ca. You can download the program, some preliminary manuals, and have fun. The source code is included. You can write your own programs in QB64, which is freely available software. And then, if I can, I'm going to stop sharing and share on the program itself and see if I can demonstrate the program. So let's try this one. No, that's the same one I had before. Sorry. Let's try that one. All right, well, there's the program demonstrating a comet hitting Earth and then debris spreading out over hundreds or thousands of years and filling all of the space between the comet's orbit, and that there's a green line for the comet's orbit. So this is the program itself running right now. As you see, it's fast enough to be interesting, and it has features such that you can change the colors of the particles. The multicolored, the green is what the comet has knocked off the planet, yellow is from outgassing, and blue are ones that have been influenced by Earth. Yellow has been influenced by Jupiter, red's been influenced by Mars, and slowly you'll get some empty spots around Jupiter and Saturn, which do knock some of the particles out of orbit. But generally speaking, you get lots and lots of orbits there. If I hit this button here, we switch to the drawing impacts. There we go. So this is a 60-kilometer comet hitting at 30 kilometers a second. And as it's calculating, it's now doing the southern hemisphere, having done the northern hemisphere. And in a second, it'll have that done. So one of the nice things about this program is it's fast. You can actually look at things in pretty quick time. There's some of the comet shapes you get for the skips. Here we're looking at 10 to 15 degrees, and you're getting ellipses. And here around 20, 25 degrees, your ellipses are becoming more and more circular until you finally out into the standard 45 degrees and things like that. You can also view it from different angles, the side of the Earth, looking head on at these impacts, the bottom of the Earth, and so on. So fun program to have to play with shapes and patterns of what you can get with comet impacts. This is the proposed Lake Michigan impact happening again in real time. And I can zoom in and show you the debris. So there's the particles going off with the comet at close to its speed. Here's the bow wave going in sideways and forwards. And there's part of the shock wave shooting things backwards. And if I were to look down here at the Carolina Bays area, in about 30 seconds, it'll start dropping stuff onto the Carolina Bays. So all these little spots here are secondary debris impact craters. And, you know, it possibly covers most of North America with little impact craters. If you were around at the time watching it, chances are something would land on you.
John, what are the Carolina Bays?
Carolina Bays are millions of depressions, elliptical in shape, all along the east coast of the United States, going from northern Florida, particularly in North and South Carolina, and on up towards Maine and New York. They are typically 4 to 10 kilometers in diameter, typically something like 5 meters deep, that they're almost flat, but they have edges, rims on the edge, which indicate that there was something pushing dirt sideways. Commonly bogs and swampy lands, and these days largely farmed and largely being destroyed by farming. That they're hotly debated as to whether they're wind erosion features, which is amazing because they're all lined up with each other for hundreds of kilometers, thousands of kilometers, and there's vast numbers of them. It's hard to imagine wind actually doing that. And when you look at maps using LIDAR, which is a really good way to do it, you see all these thousands upon thousands of elliptical shapes overlapping each other. And what we've done with the program is allow you to look at just the orientations. And indeed, you can see that there's different angles. There's a good one there. The red and the green are slightly different angles, which is also typical of the Carolina Bays. The vast majority are in one direction, and every now and then you get these other guys at different directions. So the theory is it could be done from a comet impact. Most geologists disagree and say, no, it has to be wind erosion, and I don't think there's any way wind erosion could do it. But you do get this secondary effect of all the faster debris which goes orbiting around the planet and spews out, and some of this will curve around and come back. All of the debris that goes into space is in orbit, with part of the orbit being the impact point. So all of these particles will eventually curve around here, come back here, and land where they took off from, except that the world will rotate in the meantime. So they end up over here instead, which was the opening screen of the presentation. So.
Okay, thank you very much.
Here we go.
Any questions for John? Very interesting.
I have a question, if I may. I actually lived in North Carolina for, excuse me, 3 years and had never heard of these. So I thank you for mentioning about the Carolina Bays. They certainly are very interesting formation. I also appreciate your mentioning of this alternative wind hypothesis, because, you know, in a superficial reading of the internet, that seems to be the one that's currently favored. I guess my question to you is, in terms of the falsifiability, is there no acid test that will take us in the direction towards comet impact versus wind versus some other causation?
Well, the present impact specialist community believes that the only way you can define a comet impact or an asteroid impact is if you have shock metamorphic features. So if you don't have shock cones or minerals which relate to very high pressures, then you don't have an impact. And if you're dealing with 3 kilometers and 4 kilometers a second impact secondary debris, you don't have any shock metamorphic events, none whatsoever. If indeed this occurred at the end of the Ice Age, which I think is also what happened, then most of the debris was ice. So not only do you have no shock metamorphism, you have a really strange phenomena, because lightweight thingies partly melted on their way back to Earth caused the impacts. So your whole concept of what an impact is doesn't fit the community's nature of a circle that is an explosion. These are things that land at kerplop, like you dropping a rock in mud.
You wouldn't expect shock waves at the point of impact?
You get shock waves, but they're not shock metamorphic pressures and temperatures. They're very, very minimal shock waves compared to an asteroid hitting at 20 or 30 kilometers a second.
So it's the glancing nature that limits the evidence at the point of impact.
Yep.
Now, one of the things I saw about the Carolina Bays is the timing of them. They're, I think, between 2,000 and 6,000 years old, and there seems to be a variation. Now, I know you've posited more than one impact, so that might be an explanation for that. And there's also some depositional features in terms of, you know, where those ridges form around the bays that feed into the hypothesis that it's wind. And I guess I'm just wondering, with all of this, there's the pendulum swings back and forth. How do you bring it back towards the your model?
The main group who are claiming that it's wind erosion are using measurements of the quartz crystals and the sand dunes around the edge of the craters. The ridges have sand in them, which is why they're the shape they are. They've measured radiometric stuff in the quartz to indicate its age of exposure to sunlight, and concluded that the age of exposure was thousands of years. Yeah. But most of the quartz has been buried under soil for the last thousands of years, or more recent. It isn't a sunlight event. It isn't that how old the grains were when something hit it is dramatically different than when it got hit. So yes, they've measured that the sand dunes of that area, which is the things which make the impression, you can see these low speed things hit in a sand dune more easily than on rock or other material. The sand dune itself is thousands of years old. but is the feature caused in the secondary debris impact thousands of years old is a different question. So you're trying to date wind-blown sand in a bright sky and somehow relate that to an impact, and they're not the same. The proper way to date the craters or the Carolina bays would be to do soil depth analysis and look at the number of layers of mud over the years of deposition, which you can do in lakes, but you need a variation in seasons. So as you get farther north, you get a variation in seasons. You should have age dating layers in the mud in the Carolina bays. And I've been looking through the literature and not seen anyone that actually has tried that. A couple of the bays are very big, lakes 10 kilometers across. Those should have very clear sediment layers in the bays. And I would love to go and do some age dating of the soil in the sediments in the lakes and see what they come up with. But if you take the assumption that large impacts like this cannot happen, I mean, what I'm proposing is something 40 or 50 kilometers in diameter hit the Earth recently. And what the impact community proposes is that that cannot happen in the past billion years. So we have a little bit of a disconnect between our theories and beliefs as to what's going on in the universe. If you assume that this is an impossible scenario, then you have to look for alternative suggestions, and whether or not it's a vague suggestion such as measuring the age of the sand grains in a dune and saying that's the age of the feature, or whether it's anything else, you just can't accept that you've had a 50-kilometer comet hit the Earth recently and us survive and the world survive. Not when you're claiming that Chicxulub is a dinosaur killer and it's tiny in comparison. So I have this huge conflict of interest with almost everyone else in the industry in the field, that I believe that big things hit Earth often and nobody else does.
Thank you.
Okay.
Hey, John, I have a question. First of all, very interesting presentation. I think I've asked you this last time, actually, but I don't remember the answer. I'm wondering how you became interested in this and what qualifies you to do this, what you're doing.
Well, my qualifications are a degree in physics and geology, and a really good skill at computer programming. The original interest is in the program, actually, just for the heck of it. If you study Egyptian history, you will find that there's an odd phenomena in which Luxor, whoops, oh, I've got a bug in my program. All right, can't zoom in on that. Anyhow, Luxor, which is here, was absolutely devastated in the 1600 BC era. It's assumed that the volcano Thera blew up. John Burgener's theory is that a comet came streaming across and the shockwave from the comet destroyed Luxor. The comet formed the Patera Depression, which is a 300-kilometer, 300-meter deep feature in the middle of the desert, absolutely unrelated to the geology of the area. And if you happen to have a civilization where a lot of slaves are trying to escape from the Egyptians at the time, this would be a perfect opportunity because Egypt would be in chaos and Thera would cause this wonderful tsunami to go down the Red Sea, which would cause the ocean levels to drop dramatically so that when Pharaoh was chasing you, they'd end up in the midst of the seabed while looking for you on the shore. And then lo and behold, of course, shock waves that take water away, bring it back again. And the Egyptians would get drowned. So one of the neat things of this program is I can have fun with it and do some strange programming because it's all the same effect. It's a matter of where you put the shock waves and where you put the debris being tossed. But that was what got me started. I was looking at Egyptian architecture, recognizing the buildings in Karnak and Luxor didn't make sense unless there was some incredibly significant event that occurred at 23.4 degrees, which just happens to relate to impacts from the equatorial plane hitting the Earth. And then I found these impact shapes, and then I found them all over the place. Other fun thing, totally unrelated to that, someone asked, could you have an impact hit Jupiter in a skip type system so you still have a comet to carry on? And then to create a really neat horror movie, have the same comet a year later hit Earth. And the answer is, well, yes, you can. And in fact, if you watch this one here, Earth is coming around and it's about to hit the comet in the next month or so. Whoop, coming quickly. Real time is really neat to see this stuff because it's not real time, it's 1,000 times faster. Not only can you have a comet hit Earth after Jupiter, because of the nature of dynamics of traveling around the sun, you can actually set up a scenario whereby the comet hits Earth twice after hitting Jupiter. So that too is there just as a fun demonstration of the neat things you can do with astrophysics. So my history, my original belief that large comets happen was finding a crater in Egypt that made no sense, and leading me to find lots and lots of other craters that made no sense. And as I tie it all together, it makes more sense. My justification for being intelligent enough to be able to do all this is a good degree in physics, geology, and a great skill with programming.
Okay, well, you have my vote. I'm convinced.
Thank you.
Okay, thanks very much, John. We're going to have to move on.
All right.
Yeah, very interesting. So let's go back to Shaquille, who
is he back online? Yep, there he is.
Shaquille is here.
Okay.
He's in the.
I'm in the house. Yes.
Yeah.
I'll leave my video off this time. I think I've been killing my computer. I have about 300 gigabytes worth of Jupiter data on here. So
oh, okay. Oh my God.
I'm not very happy.
I hope we get to see that sometime.
Hopefully, once maybe next year when I'm finished processing it.
Okay. Yeah.
Let me just share my screen then. Okay, so where did I leave off? I guess starting in the beginning, or here actually. So this is, I guess, the point where I finished last time?
Yep. Yep.
Okay. All right. So as I was mentioning earlier, thanks, Randy, the CME that came from this specific flare, it was a cannibal CME. It basically devoured two CMEs that had gone before it. And that's what increased the potency of it, leading to a very strong geomagnetic storm. So as I was mentioning, I was looking for a place to go and observe the Aurora, and Google Earth pointed me to this location called Peepabun. It's about just over an hour north of Mississauga. So I hopped on the 403, went up 410, up to 10 through Orangeville, and then up through 109 up to Peepabun. And Google Earth said that this is a very flat area. And this is one thing that I wanted was something which had a good sight line to the north, which is where the Aurora would be occurring. And Luther Marsh, there's a lot of trees around here, but just outside of this, it was fairly, it had a good sight line all the way around. And being south of Luther Marsh, I was hoping that there would be, of course, no light pollution as well. So it seemed like a good spot to go. So I gently threw all the cameras in the car and headed up north there. So when I got there, I got to the side of a country road and parked my car, and it was very dark. It was a very dark location. And this is just, I took a camera. I had three cameras with me. I took one camera, I just put it on the roof of my car and took a 15-second shot. I just wanted to get a view. I didn't care where I was shooting. So this image shows a plethora of stars at ISO 1600, 15-second shot, and you can clearly see Andromeda there as well on the left there, which is fairly bright, and from that location was visible via naked eye. So I set up my equipment, and this is one of my test shots as well. So this is the equipment that I had that I was using to shoot the Aurora, was a Canon 6D with a Tokina 11-16 2.8 lens, and it was set at 11 mil, and an astro-modified Canon T3i with a Rokinon 14 2.8 lens. This is actually a picture of the Canon D capturing some of the images from the Aurora, and you can kind of see, just barely make out the Aurora in the distance here. So again, very clear sight lines, so there was nothing high or there was nothing obstructing. And this was a country road here, so thankfully we didn't have any curious onlookers coming. So the picture of the aurora that I got via the 6D is this picture. From a naked eye perspective, this area was very bright on the horizon, and it had a very slight hint of green. Of course, the camera captures much more than the eye does. So none of the red, you couldn't see the reds, but you could see some of the pillars which were marching along here. So this was at the very beginning when I first started shooting. Obviously, there was some usual equipment issues initially, but I managed to work those out fairly quickly. And then towards the end, of course, for an astronomer, our good friends, the clouds came in. But the aurora itself was still very bright, and it actually sparked up again when the clouds got there. And you could see a few of the pillars moving across the sky, even behind the clouds. So you see a couple here, and you see some bright ones here as well. And if anybody has observed aurora, you know that these pillars, they start off as one, and then they split, and then they move across as well, which is exactly what these ones did as well. They moved from this direction off to this direction. So I was there for about 2.5 hours, maybe 3 hours. And this is a time lapse of that period of the auroras and then the subsequent clouds. So as they come in, you'll see the aurora start to spark back up. It gets brighter green, and then the lights come through. And then our friends the clouds brought another friend, and that was the fog. And that kind of killed off the night in the observing session. So I also had the astro modified camera as well. And of course, that's going to capture much more red. So it was not as long as a time lapse, but here's another time lapse which shows what it looked like through this camera. So the one thing about this camera, which was a bit better than the 6D, is you can actually see more structure here within the clouds, within the dancing of the aurora before the fog and the other clouds set in. Unfortunately, you couldn't see through fog or clouds. So lessons learned. I'm glad. I think this is a good location to go to, but I probably wouldn't go back to Pipabun because of the fact of the fog. So it's downstream from Luther Marsh, and based upon the wind and whatnot, I think there's a lot of humidity or condensation that happens in this area. And because of that, when I was leaving the area after the clouds had set in and the fog had set in, when I was down about this area, it cleared up fairly dramatically. And in the fact that the clouds were starting to go away, and it was fairly clear. I was almost tempted to stop, but it was already 1 o'clock in the morning, and I had to work the next day and be semi-sentient. So decided to, next time if something like this occurs, maybe find a spot down here or over here, depending on the wind. I have been north of Luther Marsh, but I have also, it adds about another 20 minutes to the ride. And honestly, when you're leaving there at 1, 2 in the morning, every minute counts to get back home. So I think an hour is about a good time to be outside of the city. And in this location is probably where I'll target next time. And if I'm adventurous, or if it's a weekend, maybe up here. But this area is a good area because it's fairly dark based upon the dark sky sites and the light pollution. This area is a good place to observe. Again, there are no parking lots, so if I would bring a telescope there, I probably wouldn't do that because you're really sitting on the side of a road in the middle of dark area. But if you want to go through with one of these type of tripods on the camera tripods, or a portable tracker, I'd recommend this area to go to take some pictures.
Shaquille, another club member had commented on the observing location of Bellwood Conservation in the parking lot there.
Yeah.
And I'm wondering if that might be, I don't know if you've observed from there, but I'm wondering if that might be another alternative location that's too far.
I looked at when I saw that email, and I looked at the light pollution map, and I found this to be, excuse me, this a bit to be. I think they have different gradations in color. You have orange, and then you have yellow, and then you have green, where the green starts, where it gets really dark, and the green, from what I understood, started around here. So there is maybe one or two. I don't know if it goes directly translate into Bordeaux sky numbers. But I found that area to be more brighter than just a bit further up. So it might be good checking out actually, but it might also yield some more light pollution, especially with Fergus and Aurora nearby as well. But good to check out those. Definitely, the more sites, the better, the more options we have to observe.
Yeah, no, Shaquille, that's interesting. That's very close to a spot where I set up to photograph Hale Bopp nearly 25 years ago. And I think the discussion we've been having online about observation places is a very important. And I think we should maybe even set up a working group to sort of analyze various places where one can go to observe and to do some astrophotography. You know, as you say, nearby, within an hour of home at least, just to make it possible for people to find and use a spot which is not private land, which is usable, but it's something that's been on my mind for quite a while. So I think I'm going to reach out to some of the people who've been talking about this for a while, and even set up a working group to come up with some recommendations. So thank you very much for this.
Yeah. Another comment here, Shaquille. You mentioned at the onset of your presentation the CME events which sparked these Aurora, of course. I'm an amateur radio operator, and we watch these kinds of events very carefully, not necessarily for the Aurora, but the effects it has on radio communications. And so this CME event coincided with a major international event that we were having with the amateur radio community, and we were quite concerned that it would completely wipe out communications, as has happened many times in the past. You mentioned the cannibal flares that eventually caught up to the CME. We actually did not experience a radio blackout. There was some minor brownouts in certain northern locations, and we surmised and then later confirmed that these cannibals events actually ate the CME and dissipated the impact of the effect on communications. It was quite remarkable. I've never seen that. I've been an operator for 30 some odd years. So things are really interesting.
Wow, that's interesting, definitely. Yeah, I saw a chart where when I think there was some, I don't know if it was through radio waves or whatnot, but she was monitoring it, and he had 3 distinct impact times where the 3 different waves hit the Earth's magnetosphere. So that was kind of interesting that he could actually discern the 3 individual impacts there as well.
Excellent presentation. Very good. Thank you.
Thank you. Any other questions for Shaquille there? Shaquille. Okay, thank you very much. As always, appreciate your excellent presentations.
Thanks. Stop sharing here.
Okay, I'm going to ask Brian Gibson to present his latest acquisition.
There we go. Oh. What did you get? Why is it giving me the wrong monitor? Let's see. Okay. You guys see that okay?
Yes, we can.
Okay. Good.
Yes, looks good.
All right, perfect. All right. Okay, so as Randy said, I've got a new acquisition. This is for my astrophotography. It's a relatively new piece of gear. I don't know if you've heard of it. It's by Sharpstar. It's basically a 130 millimeter f2.8, and it's an astrograph. So it's not really for visual. It's really for photography, although I suppose you could look through it. But it has a built-in corrector that'll cover a full frame camera, although I don't use full frame. So I've kind of recapped some of the specifications here. So 130 millimeters is basically a 5-inch. And what appealed to me as a photographer, I love fast optics. And, you know, when I saw this as an f2.8, and the focal length is 364 millimeters. So if you think of a 364 millimeter f2.8 telephoto lens, that's basically what this is. One of my favorite lenses I use for astrophotography is a 200 millimeter f2.8. So this is kind of a step up from that, but it still gives me f2.8. So it does cover a full frame camera if you use it, as I said, but in my case, I use micro four thirds, and so I'll show you in a second why, you know, that makes it even better for me. It weighs about 9.5 pounds. So I love the fact that it's very compact. It came with really nice machined rings to mount it. There's no finder, but there is a bracket on it to put a finder. It's got a great focuser that you can lock. And I got this one from Steve at Ontario Telescope. And then I just saw that Astronomy Now, which is a UK magazine, although you can subscribe to it electronically, the November issue actually has a review of this. So if you want to know more details on it, they've got a pretty good review there. So when I talk about a 44 millimeter imaging circle, which is what this has, that's what you need to cover a full frame sensor. But you can also see that you typically get a little bit of light fall off in the outer parts of the circle, and your collimation has to be bang on, especially with a fast reflector like this, especially when using a big sensor, if you want to have sharp stars all the way out here. But you can see that my micro four thirds sensor, which is the red box, is kind of using the sweet spot. So it means that the collimation was good. Like I checked it with a laser when I got the scope out initially, and it looked like it was pretty much bang on. And so for me, it's probably a little less critical that it be perfect because I'm only using this part of the image. What that also means too is that when I'm shooting, the effective focal length, this is a 2 times crop factor. So instead of 364, it's more like 720 millimeters is what I'm shooting at in terms of image scale. And again, when you talk about f2.8, just to reiterate, these are standard f-stops on a camera. And each time you go down a stop, you have to double the exposure. So if you think about telescopes, most telescopes that used photographically, a lot of them are in the f5.6 when they put a reducer on. You maybe get some at f4. Quite a few of the Ritchie-Chrétien ones are f8. So if somebody's taking a 20-minute exposure, like I saw an example of this, one of the comets, Comet Leonard, somebody took an image and they showed, oh, here's a 22-minute exposure taken with one of these scopes, f8 scope. And the benefit of f2.8 is it would only require about 2.5 minutes for me to get the same amount of light on the sensor as an f8 telescope. So again, that's just to kind of recount the benefit of faster optics. And even some of the Celestron, the RASAs, where they have the camera mounted up front, they're down in the f2 range or f2.2, so they're even a little quicker. Now it does have a filter thread, a 2-inch filter thread. Sorry? Oh, it has a 2-inch filter thread on the back of the adapter where you attach your T adapter. The T adapter thread's on here for the camera. On the back of this is a 2-inch filter thread. So if you want to use a thread-on filter, you can do it. And the corrector is installed right in the focuser. So that's the corrector. It's a doublet. One of them's an ED lens. There is, the first one of these that they brought out about a year prior was a 150 millimeter version. And there were a few issues with it that they've since corrected on this one. So the 130 has a few improvements, better coatings on the mirrors. This corrector is 2-element instead of 3, and it's got an ED lens and things like that. So they did make some changes. This is the actual box for the 130 that it comes in. So that just shows you kind of the size comparison. So this was the setup I used. And again, I've only managed to use it once. Of course, the weather this year has been terrible, and I got it out in October, one clear night. Now, I have a place in Thornbury, so that's where this is. This is actually upstairs in Thornbury, and I have a deck off of here. So literally what I do is I set this thing up on the deck just out the door here, and I have visibility to the north and the east and overhead. So it's great for doing my polar alignment. I can come inside and, you know, let it continue to take images outside and that sort of thing. But this is an Ioptron CEM 40 mount. So it's basically a 40-pound capacity mount. And as I said, the scope only weighs about 9.5 pounds. And the only thing I've really added to it here is the camera, which is, again, Micro Four Thirds cameras are very small. This is an Astro modified, or full spectrum modified camera. Not that it would have made too much difference on my subject. And I have a clip-in filter in the body. So that's why I'm not using a 2-inch thread-in filter, but this is my T adapter and the camera. And it was very easy to focus. The focuser is great. It's got the fine focus and you can lock it, as I said. So once I got it focused, I locked it. And then all I was doing here for this, I decided that I would do M33 as my first little target, just as a test. It was pretty good conditions. There was no moon up yet. The moon hadn't risen yet. So M33 was maybe up about 45 degrees. Again, looking east, I have a clear sky. And anyone that's not familiar with the location, if you know where the Andromeda Galaxy is, basically follow it down through these couple of stars, and it's about the same distance south of Mirage to the M33. And up there, M33, it's Bortle 4 skies, so I can see the Milky Way fine. The skies are really good there. M33, I usually look at it with binoculars, and you can't see any detail, but you can always pick it up as kind of a smudge, because it's actually quite large. It's about 2.5 times the size of the full moon, even though it's really faint, has a low surface brightness. But it's generally visible in binoculars without too much trouble, just that you can't see any detail on it. So this was my image, my first round. And this is really just a 10-minute exposure. So this was 10, I had set it up. I didn't have auto guiding running, so this was just unguided with the mount. That mount has I-polar, so you do a polar alignment with the camera on the mount, which I did. And it seemed to be tracking fine. So I was just doing 10 60-second exposures at 1600 ISO. And I added one dark frame into it. So this was just kind of a test. I did take some other frames that I haven't played with yet, but you know, I was reasonably pleased that it picked that much up in 10 minutes. And I used Lightroom and Photoshop was all I used in this case to stack them and process it. So, I mean, overall, I'm really happy with it. Just wish I'd get a few more clear nights to get out there. I'd love to point it at, if I'd pointed at something where there was more hydrogen alpha, that's where the full spectrum camera would have made a difference. Even with this object, it obviously needs more time. But, you know, the stars seem pinpoints to the corners of the field and everything. So overall, like I said, it's a great little addition. And looking forward to using it in the summer when you got a lot more of the emission nebula and stuff to shoot at. So I'll leave it at that. Like I said, there's a great review in the November Astronomy Now magazine too, if you want to know more about it. Any questions? You guys still there?
Yes.
Oh, okay.
Yes, definitely.
I was just worried. I thought, oh, damn it. Did it freeze halfway through and I've been talking to the wall? No, that's great. Okay.
No, thanks, Brian. No, that was awesome.
I'll stop my sharing. Yeah. I got worried for a minute.
Yeah.
Wouldn't be
No.
the first,
What's
wouldn't be-
the what's
it
the
wouldn't be the
focusing?
first time I've done that.
Yeah,
Brian.
technology, right?
Yeah.
Brian, what's the focusing like for that? Is it difficult to focus, or do you have a motor
I
focuser?
would actually, because I initially focused it in the day just to kind of see. I put the camera on and pointed it across the street, you know, at some of the rooftops. And no, it was very easy to focus. And then what I do, again, with the mirrorless camera body, I zoom in. Like I can zoom in, I think 10 or 14 times.
Yeah.
And with the fine focus on there, it actually was quite easy. And then I literally locked the focuser. So it's got a 2.5-inch focuser. It's pretty heavy duty because it is made for photography. So I don't think you'd have any problem even with a heavier camera on there.
Cool. Sounds nice. I'm anxious to see some of your future work.
Yeah, I look forward to using it more. Yeah.
Yeah, I know it's been a challenge with the weather for sure.
Okay, any other questions for Brian? Okay, thanks very much, Brian. Excellent. All we need is some good weather, right?
Exactly.
That would be nice.
Maybe in the spring.
Yeah.
Well, we got to have good clear night for the eclipse, right?
Yeah. That's what I'm trying to
That was your segue.
share with you. Yeah. Do you see?
Yeah.
Do you see my presentation?
We see the helix, I think, or
Nice helix.
It looks like a giant eyeball.
Yeah.
What? That rather sucks.
You were intending something else.
Yeah, Hank, stand by. Okay, let's try this. Hope I can share this. Do you see my presentation now?
yeah.
Yes.
See all the slides. There's 12 slides visible. That's good.
Okay, good. Oh, whew. Technology nearly wins again. All right. Yeah, let's finish off just to talk about next week's eclipse. And it's nearly total. And I've seen more and more articles about how next Thursday's eclipse is the longest lunar eclipse ever. And I'm pulling out what little hair I have left, because it's not quite a total eclipse. So it's essentially a partial eclipse, but it's not the longest total eclipse ever. So yet again, online idiots don't know what they're talking about. But anyway, let's talk about what we can see next Thursday night. So lunar eclipses. Boy, I don't know how many times I've talked about lunar eclipses in my my career with the center, but we've seen quite a few, and that's because you get at least 2 lunar eclipses every year. But they are not necessarily visible from where you are, but they do in fact have to happen. And in just to summarize, a lunar eclipse is when the moon moves into the shadow of the Earth. The Earth and the moon get our sunlight from the sun. And if the moon at full moon happens to move into the shadow of the Earth, then we lose sunlight on the moon and we get an eclipse. So full moon is at the point where the Earth is in between the sun and the moon. And normally we get a nice full moon and nobody hears about an eclipse, but every now and then things line up and we get an eclipse of the moon. So the moon, moving in its orbit here from right to left, moves into the penumbra and umbra of the shadow of the Earth. And those are just terms which mean that when the moon is in the penumbra, it's partially covered by the sun or by the shadow of the Earth. And then in the umbra, when the moon is in the umbra, it is totally covered by the Earth and it no longer receives direct sunlight from the sun. So we have a full moon every month. Why don't we have a lunar eclipse every month? It's because that the angle or the inclination of the moon's orbit is 5 degrees to the sun-Earth orbit. So most of the time, the moon is above or below the shadow of the Earth. For a new moon, it's above the shadow of the Earth, and you don't get a solar eclipse. And it's above or below the shadow of the Earth, and so it passes above or below the Earth of the shadow of the Earth, and we get a full moon. So 5 degrees isn't much, but it's just enough to make eclipses not all that rare during the year, but we don't get them every month. We only get them once every 6 months. And that is when the line of nodes of the inclination of the angle of the full moon or new moon orbit coincides with that of the Earth-Sun orbit. Boy, this is getting complicated. But essentially, every 6 months at new moon and full moon, everything lines up. We get an eclipse of the sun, we get an eclipse of the moon. So every 6 months, that happens. We had an eclipse of the sun last June 10th. We're getting an eclipse of the sun in a few weeks in early December, total eclipse down in Antarctica, and the same thing with lunar eclipses. So you have to have an eclipse every 6 months only because everything lines up nicely at that point. All right, for this particular eclipse, the full moon is moving into the Earth's shadow through the penumbra and the umbra, but it is not passing through the umbra 100%. It's missing the umbra by a few percent, which means that the eclipse is not total. It means it's partial. And from that, news websites are saying that this is the longest eclipse of the moon ever. Not because it is the longest eclipse of the moon ever, but it is a long partial eclipse. That being, the moon is passing through the umbra, but only 97%. So they're saying from 7:18 UT to 10:47 UT, it's the longest eclipse ever, which is rubbish. So, but anyway, enough of that. Yeah, I mean, I just lose so much patience. So what it means is that the moon will be 97% total, which is essentially total by any means. But that's what's happening. So the moon enters the umbra at 6 o'clock UT, subtract 5 hours to get our local time. It moves into the umbra to start the partial eclipse at 7:18. Penumbral eclipses are hard to observe. You can see them if you really try, but it's the partial eclipse that's more interesting. Moving into the umbra, we get mid-eclipse at 9:03, which is 4 in the morning. And at that point, the moon should have a reddish cast to it. We'll talk a little bit about why that is later. And then it continues to move through the umbra into the penumbra. Partial eclipse ends at 10:47. Essentially, the show is over at 5:47 in the morning. But for all the diehards, you can wait until 7:06, which is probably about moonrise for us. So lunar eclipses happen at any time of the day or night, but not necessarily that we can see them. So the odd time a lunar eclipse will happen during the middle of the day. If the moon is not above the horizon, you don't see it. Anytime the full moon is above the horizon for you during a lunar eclipse, you will see it. That is the rule. So for the November 19th eclipse, you see the same kind of diagram, the moon moving through the penumbra and umbra, but the diagram at the bottom is really, really interesting. And it kind of took me a while to become familiar with this diagram. And what this diagram shows is who will be able to see the November 19th eclipse. Essentially, if you are in this white area, you can see the entire eclipse. But as I said, if the sun is above the horizon for you during the eclipse, you can see it. But because the eclipse takes like 5 hours to take place, for many places the moon will set during the eclipse, and for other places it will rise during the eclipse. So they have these different labels: P1, U1, U4, P4. And if you go back to this is P1, U1, U4, P4, or whatever. So the 5 different stages of moving through the eclipse: penumbra, umbra, total or near total, umbra, penumbra. So if you're anywhere in this area, you see the entire eclipse. And we see the entire eclipse for this particular eclipse. And this, in fact, is the overhead point of maximum eclipse, so just off the island of Hawaii. If you are in this area here, the moon sets during the eclipse, during the partial phases, the umbral phases, the penumbral phases here. If you're in this area here, the moon rises during the penumbral phase, the umbral phase, and the penumbral phase. So essentially, half of the planet always sees the moon, but during a lunar eclipse, more than half the planet has an opportunity to see the eclipse. This area here will not see any of the eclipse. This area here will see all of the eclipse, and then this area here and this area here will either see the moon rising or setting during the eclipse. So that's how that works. And what's interesting is that these lines change depending on whether we're close to a solstice or an equinox. If it's close to an equinox, they'll be very, very straight up and down. And if they're slanted somewhat, then you're getting close to a solstice. So here we are on November 12th or November 18th or whenever it is, 19th. We're getting closer to a solstice, and that's why they are more curved. And that's why you have all of the area of Antarctica being in the dark and some of the Antarctic being light, which doesn't make sense because that, of course, is, oh, that's for viewing the moon. So all of the Arctic area will be able to see the moon because it's at a high declination, and a lot of the Antarctic will see nothing because it's at a low declination for them. So yeah, so it's kind of, that's why it took me 20 years to figure this diagram out. So for us here, the moon eclipse starts at 1:02, not much to see. 2:18, the umbra phase starts. This is Thursday night, Friday morning next week. Greatest eclipse is at 4:02, and partial eclipse ends at 5:47. So if it's clear, you want to see the eclipse, I would suggest you set your alarm for 4 o'clock and go out and take a look with binoculars. If you're really keen, then watch it from 2 o'clock to 5 o'clock. If you're really, really keen, stay up all night. But I do remember my very, 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 very first total eclipse of the moon I saw in February 1971. I got up I set the alarm for 2 o'clock. I went out in my pajamas, saw the eclipse, looked like a red hot penny, went back to bed. So that was my first eclipse. And I would suggest that this is your first eclipse, do the same for 4 o'clock in the morning. So what is it going to look like? This is a moon moving into the penumbral phase of an eclipse. So you can see not all this exciting, but you can see some shading. So what this means is that the darkish areas of the moon, if you were standing there, you would see the sun partially eclipsed by the Earth. Moving into the partial phase, if you were standing on the moon where the darkish area is, you would see the Earth totally covering the sun, but everywhere else you would see the sun partially covered by the Earth. And as the moon moves into the umbra of the Earth, you get more and more of the sun, of the Earth, the moon essentially disappearing. Now, if the Earth had no atmosphere, then at total, when the moon was totally in the umbra, you would see nothing. The moon would be receiving no sunlight whatsoever. But because the Earth has an atmosphere, the sunlight refracts through the Earth's atmosphere, and essentially everything that causes a reddish sunrise or sunset, that light falls upon the Earth, and we get a beautiful reddish moon. So this is a picture of the 2010 eclipse moving slowly into totality, and you can see that there's still some sunlight falling on the Earth, but there's also some refracted sunlight, the reddish reflected sunlight falling on the moon, and you can see some stars. And this was actually taken from my driveway in Mississauga. So this is the kind of stuff that you can, in fact, photograph. This is also from 2010 during totality. And the interesting thing is that the shadow of the Earth towards the center is darker, and to the edge is lighter. It's not a straightforward shadow. And in fact, as the moon moved out of the shadow, you could begin to see different shading of the moon. Now remember, this isn't a total eclipse. This is a very large partial eclipse, but not total. But this is what we'll see as the moon moves out of the shadow of the Earth on Thursday, probably after 5 o'clock sometime. Now, just to go back, I went back and looked to see, because I remembered an eclipse which was not total, but very, very close to total. Back in 1997, it was 91% or 92% total. This upcoming one is 97% total. But this was an eclipse that was nearly total. And this is a picture I took during maximum eclipse. So you can see that you can still see a large amount of reddening in the umbra, but you can see a fair amount of the northern part of the moon outside of the umbra. So, you know, shift this to the southern part, and this is 92 versus 97. So we're going to have a southern part of the moon still outside of the umbra. But I still think we have a good chance to see the reddish part of the moon during the maximum. So again, it's never total. It's always partial, which is why it's the longest lunar eclipse of the century, due to some media reports, which you know, is bogus. But the really neat thing about this eclipse back in March 1997 is that 180 degrees behind me was Comet Hale-Bopp. And it was sitting in the sky just off from Cassiopeia. And this is from Mississauga. And after a while, we really got used to seeing this comet in the sky because it was so brilliant, so beautiful. And the fact that I was able to see it during this eclipse was really amazing. And if that's a view from the city, you can imagine what it would have looked like from a darker sky site, like where Shaquille was for his Aurora pictures, because that's where we went in April. A few weeks after this eclipse, we went up there in April 1997 to take pictures of the comet. So good luck, everyone, and I hope you have clear skies next Thursday night. But don't make the mistake I did years and years ago when they announced that the eclipse was on November 19th, but it was the early morning. It was the night of November 18th. So don't make that mistake, because you can be 24 hours late if you make that mistake. So that's my presentation, and are there any questions? Okay, well, good luck. And are there any comments, questions, anything before we sign off tonight? It was a really excellent presentation, and I'd like to thank everyone for all the presenters for coming forward tonight. A lot of great information. As I say, we're continuing to look at returning to UTM. It's going to be a while, but I think the meetings that we hold online are still working out quite well.
Merry Christmas and a Happy New Year, everyone.
Yes, thank you. So we have a meeting in 2 weeks. John Reed from the Halifax Center will be giving a presentation, and we have a December meeting as well. So we're looking forward to seeing you then. But otherwise, take care, everyone, and all the best.
Good night.
Good night.
Thanks, Andrew.
Good night, and thanks to all the presenters. Good night.
Yeah.
Hey, everybody. Great presentations.
Yeah.
Thanks.
Take lots of pictures of the eclipse.
Indeed.
Good night, everybody. Thank you very much.
Bye-bye.